We'll now talk about the Part B, another quantitative experiment. Remember, Part A and B both involve accuracy grades. We're going to be decomposing potassium chlorate by heating it over a flame. We'll make our very careful measurements and come up with three very important weights: the weight of a test tube, the initial weight of our reactant, and the initial product or the final product weight after the heating. So here, just to kind of remind ourselves, this is an experiment we've also done before, where we weigh it, cook it, weigh it again, weigh it, cook it, weigh it. We are using a test tube to hold the reactant of potassium chlorate. Chlorates, we've learned, according to our helpful hint page, decompose when heated to release oxygen gas. So we're letting go of some oxygen. Remember, the combination pattern from Part A is a building pattern. The decomposition of Part B is a breaking it down pattern. One reactant breaking down into simpler products. So here we have being asked to calculate the mass of the initial reactant. We know that the mass of the test tube minus the potassium chlorate in the test tube would be a simple calculation. 14 grams minus the 10 grams of the empty tube gives us 4 grams of the initial reactant, potassium chlorate, KClO3, potassium chlorate. Easy enough. We'll calculate the mass of potassium chloride produced after the reaction is complete. So let's go back to that data table and see what we had. Here's the mass of the test tube after heating. Now remember, this test tube has a residue inside. It's a dirty test tube. At the very end, potassium chloride is in the test tube. It's not a clean test tube. That's line number 1. So the mass of the test tube after heating includes the potassium chloride because the oxygen gas is leaving the test tube and going out to the atmosphere. So this is the calculation we need for that next number 2, 12.5 grams minus 10. And that, of course, shows 2.5 grams of potassium chloride. Potassium chloride is left as a residue. So this, just to remind yourself, this is the solid form in the tube. So therefore, if we know in the test tube, initially we had 4 grams of potassium chlorate and 2.5 grams of potassium chloride, how much must the oxygen be? So here we have the whole compound. Here we have one of its pieces. That missing weight must be the grams of the oxygen released to the air. So here we have 4 minus 2.5. And that, of course, is 1.5 grams of oxygen. I'll just make that a little neater for you. Grams of oxygen. Calculate the mass percentage of potassium chloride produced from this experiment. The percentage is its part of the mass over the whole compound. The grams of KCl we determined to be 2.5 grams out of the original reactant, which weighed 4 grams. Express that as a percent, and what do we find? 62.5% by mass is that solid residue in the tube of potassium chloride. Of course, then the molecular oxygen that left the tube, and I suppose I should have come up here and put O2 because this is molecular oxygen that's leaving now, is no longer part of our compound. When it escapes as a gas, it goes to its molecular form. So the molecular oxygen escaping to the air weighed 1.5 grams out of that original mass we started with of 4 grams, and express that as a percent. And of course, it should be the difference of 100 minus 62.5, or 37.5% by mass oxygen. The correct formula for potassium chlorate is KClO3. Using molar masses, let's calculate the theoretical percentage of oxygen in this compound. So not from mass data, but from actual percent data using atomic weights. So here's what we're saying. KClO3, potassium has a molar mass of 39, chlorine has a molar mass of 35.5, oxygen has a molar mass of 16, but there's 3 of them in this formula for a total contribution of 48. So from here, let's sum those. 39 plus 35.5 plus 48 gives us a total value of 122.5 for the compound's formula weight. So our percentage of oxygen comes from part over whole. And we'll express that as a percent. 48 divided by 122.5. I didn't hit that right. Let me try again. Sorry. 48 divided by 122.5, and that's 39.2%. So here's what we called our experimental value, what we got from generating numbers in the lab. This is what we call our theoretical value. These are the numbers that we got from using the periodic table. How close are they? It gives you an indication of some accuracy in your report. 37.5 and 39.2. So I'm just writing those down. As I go to my next page, it wants to know the percent error. You're expected to remember this formula, so study it. Percent error. Experimental minus theoretical. Remember, subtract those either way, but make it a positive number. Error is always positive. Divide that out by the correct answer and multiply by 100 to find its percentage. So the 37.5% minus the 39.2. Now let's remember where those came from. From our experimental 37.5, from our theoretical 39.2. So on the bottom, we have the 39.2. So it's the difference between the two divided by the correct answer. Remember to ignore the negative. Now let's hit this together and see what we find. Times 100. This experiment came out with a 4.3% error. The complete balanced equation started with a reactant of potassium chlorate. You will be expected to put those adjectives on. You heated that strongly to force a decomposition, leaving a residue of potassium chloride and releasing molecular oxygen into the air. This will require coefficients to balance your equation. Part A, combination. Part B, decomposition. They are both quantitative, number crunching lab components. Pause this video right here. Practice the data table until you become confident that you can do it without any help. Then move on to part